All right, so let me show you. First of all, you should know this because you may be caught on a desert island someday without an ohm meter. And so if you need to know the resistance values of resistors, here's a resistor. It has an orange, a white, and a brown band. And so the orange band is 3. The first digit is a 3. The second band is a white band, which is a 9. And the third band is a brown band, which is a 1. Okay, now what that means is this resistor is 3, 9 times, this is a multiplier band, times 10 to the first power, which is 10. So 39 times 10 is 390. So this is a 390 ohm resistor, give or take 5%. The fourth band is a tolerance band. It's either 5%, 10%, or even 20% if there's no band. So if we take our ohm meter and connect it, we see that this resistor has a value of 0.390. How about that? 0.390 kiloohms, which is 390 kiloohms. So it has the exact resistance that it says it has, which is very unusual because they're not usually that accurate. So what you need to do before you put these into your printed circuit board is to measure all 3 resistances and note down the color code so you can tell one resistor from the other. So I'm going to put that resistor in this column and in this column. Okay. Now, as you have seen from your write-up, and maybe you haven't seen that lately, let's just take a look at how this PC board works. First of all, there's a little metal clip underneath this column which connects, it's like a little spring clip. When you push the wire in, it spreads that spring clip apart and it connects each one of these, the wire that you put in each one of these to each other. So this wire is not connected to anything right now, but it will be. For instance, if this is V1, if you look back at the diagram, and this is the positive side of my V1, which I'm picking as roughly 6 volts, if I plug this red wire into the same column, it doesn't have to be next door, in the same column that this lead is in, they're connected together. You don't have to twist them together, you don't have to pinch them together. They're pinched together by that little clip underneath these. So this, if you look back at the circuit, this is the connection between voltage source V1 and resistor R1. So this is resistor R1. Now let's take another resistor. This resistor is gray, red, and brown resistor, which is 8, 2, again times 10, so it's 820 ohm resistor. So let's see what it is. It says 810 ohms. So take that, not this, because this is roughly, plus or minus 5 or 10%. So this is an 810 ohm resistor. I'm going to make this resistor R3. So I'm going to put it in that same column, and these are not interconnected with these. So there are 2 separate sets of 5 connections. And so if I plug that in somewhere down here, any old place down there, and I plug this black wire, which is the negative side or the ground side of resistor of voltage source R1, I now have completed the left branch of the circuit, V1 through R1 to R3 back to V1. This is a nice current loop. It looks much more messy than it does on the board, but that's what it is. So now I need an R3 resistor. This R3 resistor is, this one's a little hard to see. This is violet, green, and brown with a gold band, which means plus or minus 5%. So 5 times 10, 750 ohms. So let's check it out before we put it in, or probably you should check it out way ahead of time and write these down. So this is going to be 766 ohms instead of 750 ohms. So this is going to be R2. I plug this into the same column that R1 and R2 are plugged into, and I'm going to hook up our V2. V2 is the voltage source going to resistor 3, and it goes to the this goes to the bottom side of resistor R3. So that, believe it or not, is the same thing I had on the board just a minute ago. This is V1, this is R1, this is R3, this is V2, this is R2. So that is the circuit that we have set up. Now what I need to do is measure. All I need to do to apply Kirchhoff's rule, since we've measured the 3 resistor values, is to switch this over to voltage and measure the voltage of V1 while the circuit is in operation. Okay, well, this is a little unnerving. It shouldn't read anything. So this meter reads 0.03 when it should read 0. That's very interesting. It may need a new battery. So let's measure the voltage V1 when V1 is operating the circuit. So I'm going to touch my black lead to what I'm going to call ground here. That's the junction where the 2 black wires come together. And I can touch the red lead to this wire here, and I get my voltage V1, my operating voltage V1, which is 6.31 volts. So quite a bit different than just plain 6 volts. And to measure V2, I do the same thing, connect this to the junction where the black wires come together, and this over here, and I get 4.56 or 4.57, somewhere in between. That voltmeter samples every half a second, and so it's kind of deciding whether it's 6 or 7. I'm going to call it 7 because it's 7 more times than it's 6. So 4.67 volts. So V2 is 4.67, V1 is whatever I said, 6.30 volts. So that's all I need. That's all the numbers. I've got R1, R2, and R3, and V1 and V2. So I'm ready to do Kirchhoff's rules analysis, and I'm done with the Kirchhoff's calculation. But now I want to do the Ohm's law calculation, which is the easier one. Again, I'll put this on a voltage setting. To use Ohm's law instead of Kirchhoff's laws, I measure the voltage across a resistor and apply I equals V over R. I'm going to use Ohm's law to figure out the current through this resistor as a check, and so if I put these probes on these two, I get 1.972 volts. You notice I had it on a 2 scale, which means I get an extra decimal point in the third decimal point there. So 1.973 volts. And you also notice that that's plus. If I reverse the leads, I get minus 1.973 volts. What that says to me is that since Ben Franklin current goes from plus to minus, when I hook it up this way, the current is going this way. So I can actually tell that the current's going that way in that resistor. I kind of knew that from the way I set up the circuit, but sometimes you don't. And it's 1.973 volts. So if I take this resistor value and divide it into 1.973 volts, I get the current through that resistor. Okay. So that's I1, I2. Again, hook this up. I get a minus there, 0.2. So that means the current goes this way. So if I want to reverse it, the current goes 0.221 volts. So I can calculate the current I2 there using Ohm's law again. I equals V over R. And also I can calculate I3. Okay, now my meter shows a steady 1, which means it's over 2 volts, which means I have to switch it to the next higher scale. And when I do that, I get 4.35 volts. So that's it. And if you think along the lines of Kirchhoff's loop rule, this voltage here was 6.3 volts. This was about 2.0 volts. This was 4.3 volts. 2.0 plus 4.3 is 6.3. So the voltage produced here is dropped here 2.0 volts roughly, and the rest of it's dropped here 4.3 volts back to 0. So my little Kirchhoff's loop rule, it all makes sense. 6.3 minus 2.0 minus 4.3 is 0. Okay, so then we'll do that for R2 and R3 and calculate using Ohm's law the current through those resistors. Again, the direction is determined by from red to black. So this should be positive, and this should be positive. Okay, yes. That's it. Very simple. It's easy to take the data. To do part B, we just switch a couple of these resistors, change some of the voltages. You can even make them go the other way instead of positive this way, positive that way. Whatever you want, it works with any voltage, with any resistor, with any current. Kirchhoff's laws work all the time. So again, your error is based on your error as given in this little booklet of error in the resistance and the error in the voltage as measured. That's your error analysis. Pretty simple.